everyone. Last time we tried to understand what is the directing effect of a group of electrophile in the benzene ring. Basically, we were trying to understand how we will be able to write the product when there are multiple substitution reaction on benzene. That means you already have a substituent, you already have an electrophile on the benzene, and now you are adding, or the new incoming electrophile is coming to get substituted. Now the discussion what we had, the crux of it can be presented like this. I will review whatever we discussed last time, and then from here we will carry on the problem solving for this topic. What we discussed last time, and I drew two resonating structure, and you must be convinced from that two resonating structure is the withdrawal and the donation or the pumping of electron is only at ortho-para position. This you must understand, and this you must know, and this you must convince yourself by drawing resonating structures. So electrons are withdrawn from ortho-para position and electrons are pumped to ortho-para position. Meta remain as it is. Alright, this we saw, and this I hope you are convinced with. Next thing that you need to understand is, how, given a group, how would you identify whether that group is electron withdrawing or that group is electron donating or electron pumping? Because based on this characteristic you will be able to find out the position of the next incoming electrophile. So to know this, we must know, or we must look at the atom which is directly attached to the benzene ring in that group. If that atom is electron rich, then electron will be gushing into the benzene ring, making that group electron donating, and if that atom is electron deficient, then the benzene electronic density from benzene ring will be diffusing out into that orbital of that atom, making that group electron withdrawing. Now once you identify whether the group is electron withdrawing or that group is electron donating, then you can identify the position of the next incoming electrophile, because the electron donating group will be ortho-para directing and electron withdrawing group will be meta directing. Now why should that be so? I told you, I will recapitulate that. That happens because when a group is electron withdrawing, then this is the RS that we get. If this group is withdrawing electron, it will withdraw from ortho-para position. That will bring about certain amount of plus charge density at ortho-para position. And if a group is electron releasing or electron donating or electron pumping, as I say, then there will be electronic density at ortho-para positions. So there will be increased electronic density at ortho-para position. So whatever it is, whether it is withdrawal of electron or donation of electron, it is at ortho-para position. Now suppose this group is electron withdrawing. Now if this group is electron withdrawing, then there will be some developed positive charge at ortho-para position, and if a new electrophile has to come, electrophile means electron loving, so it will go to the site where you have highest electronic density. And the site which is having more electronic density here is meta position, because meta is neutral and they are electron deficient, ortho and para. So this group will be meta directing, meaning it will direct a new incoming electrophile to meta position, or rather the incoming electrophile will automatically go to meta position without any direction, but still we say that's the directing effect of group G. And if the group is ortho is electron donating, then it would have increased the electronic density at ortho and para position by its donation of electron, and now a new incoming electrophile will go to ortho para, because ortho para is more electron rich than meta. So a group which is electron donating will be ortho para directing, because it has increased electronic density at ortho para position, and a group which is electron withdrawing will be meta directing, because it has decreased electronic density at ortho para, and hence meta becomes more electron rich than ortho para. That's it. So here in this case the group will be meta directing, and in this case the group will be ortho para directing. So ortho para will be of one category and meta will be of one category. If a group is increasing electronic density at ortho, by virtue of resonance it will also increase electronic density at para. So ortho para will always come together and meta will be in one group. Now the whole job is to identify the nature of the group. So to have a practice before we move on to the actual problem solving, I'm giving you some group and you try to identify whether that group is electron withdrawing or electron donating, or in other words whether that group is meta directing or ortho para directing. To begin with, let's start with humble benzaldehyde. Now if our electrophile is coming to benzaldehyde, now the question is, where will it go, to ortho para position or to meta position? Now to do this, all I have to find is, I have to find the nature of this aldehydic group. If this aldehydic group is electron donating, then based on the discussion up till now, the new incoming electrophile will be going to ortho para position. If this aldehydic group is electron withdrawing, then the new incoming electrophile will go to meta position. Now how would I identify the nature of this group? I have already told you how to identify. I do it again for you one last time. This is benzaldehyde. If you look at the atom which is directly attached with the benzene ring, that is carbon, look at carbon and try to identify whether that carbon is electron rich or electron deficient. Carbon have no lone pair, so carbon is not having any electron richness by virtue of lone pair. Carbon, on the contrary, is electron deficient because this oxygen happens to be second most electronegative atom, so this will pull most of the electronic density from the double bond towards itself. So carbon will be left with less electronic density, that will bring about electron deficiency in that carbon. Now carbon will plea to the benzene ring and ask for electronic density, and this generous benzene ring will diffuse its electronic density towards the empty orbital of carbon. So this group will become electron withdrawing. That's the general rule. You don't have to think much of anything much more than that. You look directly at the atom which is attached to benzene ring, look at that atom and find whether that atom is electron rich or electron deficient. If this atom is electron rich, electronic density will move into the benzene ring. If it is electron deficient, electronic density will move out of benzene ring, fulfilling the deficiency of that atom. Here it is electron deficient and here it will be meta directing. Alright, this is how you have to go about it. Let's solve some more, and this time you try to answer whether the group will be electron meta directing or ortho para directing. Let me give you an easy one. Phenol. You have to find about OH. So OH will be ortho para directing or meta directing. Similarly in aniline, NH2 will be meta directing or ortho para directing. If you have acetophenone, so the new incoming electrophile will go to meta position or ortho para position. Similarly, suppose we have benzoic acid, or we have cyanobenzene or benzonitrile, or we have nitrobenzene. Or we have ethynyl group to benzene, or we have a ester group to benzene. So in these compounds you have to find if a new electrophile is added on this substituted ring, where that electrophile ought to go, at ortho para position or meta position. Now in the first compound, like what you do is you properly write your answers down, and then we will discuss about the answers. You without practicing is not going to improve you. So better write down your answers and then play up the video and look for the answer. For phenol all we have to do is look at the atom directly attached with benzene ring. Here we have oxygen. Oxygen, we know that oxygen has 2 lone pair. So this is pretty electron rich, oxygen having 2 lone pair. So of course electron of the oxygen will be pumped into benzene ring, so OH will be electron donating group, so OH will be ortho para directing group. No problem there. Similarly, in aniline you have nitrogen. Nitrogen electrons will not be drawn like this, but you have to know that nitrogen has a lone pair. So nitrogen has a lone pair, so nitrogen's lone pair will be pumped into benzene ring, increasing electronic density at orthopara, making it orthopara directing. Look at this carbon. This carbon, whenever carbon is attached with oxygen, now the carbon oxy double bond O is always electron deficient, because the electronegativity difference between a carbon and oxygen is huge. Oxygen is the second most electronegative and carbon is second least electronegative after hydrogen. So that because of this increased difference in electronegativity, the most of the electronic density of this double bond will gush towards the orbital of oxygen, making carbon electron deficient, right? So this carbon will try to get electronic density from benzene ring, pulling the electron out of benzene ring from orthopara, making meta richer than orthopara in terms of electron. So the new incoming electrophile will go to meta position, making this group meta directing, right? So this is orthopara directing, this is orthopara directing, this is meta directing. Same will be the case with the carbon of benzoic acid. Carbon of the carboxylic group in the benzoic acid. The carbon is attached with 2 oxygen, and both the oxygen will be just pulling up the electron from carbon, making it helpless and asking for electrons from the benzene ring. So the whole group will be termed as electron withdrawing, making it meta directing. Similarly, if you look at the carbon in the cyanide group in benzonitrile or cyanobenzene, then the carbon is attached with nitrogen, the third most electronegative atom of the periodic table, through 3 bonds, and nitrogen will be pulling the electronic density from all the 3 bonds, making this carbon sufficiently electron deficient. So the electrons will gush out of benzene ring again to the orbital of carbon, making the cyanide group electron withdrawing and meta directing. Now we have NO2. Now nitro group is a very powerful electron withdrawing group. It is so powerful that it withdraws such a huge amount of electronic density out of benzene ring that not much of the electronic density is left over for the new incoming electrophile. So the rate of reaction is reduced to a considerably very less amount when a nitro group is attached with benzene ring. This will have a very important consequence as we move ahead in the topic, and later on we will not carry out any electrophilic addition reaction whenever we have a benzene on a whenever we have a nitro group on benzene ring, because when you have a nitro group in benzene ring, the electron withdrawal is very huge and the electronic density in benzene is very less to offered to incoming electrophile. So the rate of addition or the rate of substitution on benzene ring is considerably reduced. So NO2 is a very powerful electron withdrawing group. The reason being, there are 3 very electronegative atoms attached here. There are 2 oxygen pulling the electron from nitrogen, and the nitrogen will be pulling the electron from benzene ring. So there will be a cumulative effect of 3 very high electronegative atoms, and that cumulative effect will result in very high electronic density withdrawn from the benzene ring. So NO2 will be a very powerful electron withdrawing group, making benzene ring very much electron deficient. And if ever, or if with whatever rate electronic substitution of a group has to take place, or substitution reaction has to take place on nitrobenzene, of course it will occur at meta position, because from ortho and para huge amount of electronic density has been withdrawn. Okay, then we have ethynyl group attached with benzene ring, and here you have to say whether this group will be acting as meta directing or ortho para directing. The first point, that let's have this discussion after this, at last we'll discuss what will be the case here. If you look at this ester group, again will be meta directing, because the carbon is again electron deficient. However, the electronic deficiency of this carbon is much less than that is in the case of a ketone or aldehyde, because when this oxygen, the oxygen of C double bond O, pulls away the electronic density from carbon, you have a oxygen with lone pair that gives its electron into the orbital of carbon. So when this carbon seeks help from external source, both this benzene ring and this oxygen comes up with the help giving its electron to the carbon. So this carbon is sort of getting help from both the groups, this OR group and this benzene group. So the effective amount of electronic density pulled out of benzene ring will be much lesser than what is there in acetophenone. So if you talk in terms of rate of reaction, then the rate of reaction in this ester will be much higher than the rate of reaction in this acetophenone, because the withdrawal of electron from benzene is considerably less, because carbon also has another source who can supply electronic density. Here we don't have any other source, because here carbon do not have any electron to pump into the empty orbital of this carbon. Now let's talk about this. What will it be, ortho para directing or meta directing? The point is there will be no electronic substitution of any electrophile in this case. The reason being, we have a pi bond outside the benzene ring. Whenever we have a pi bond outside the benzene ring, then the rate of reaction on the pi bond outside the benzene ring is multiple times greater than what is there in the benzene ring itself. Generally we have a substitution on the benzene ring, because the RDS to be crossed in a substitution on the benzene ring is very hard to cross, because remember, in RDS aromaticity is broken, and in case of addition, when you are having on any other normal pi bond, then the RDS do not have to be broken, and it is comparatively easier for the RDS of this pi bond to be crossed than breaking the aromaticity. So when you have a pi bond outside the benzene ring, then the electrophile prefer to get attached on this pi bond rather than on the benzene ring. So preferably the addition will be on the pi bond and not on the benzene ring. So here there is no question of substitution on the ring, rather the addition will take place outside the ring. So here we really don't discuss whether it is meta directing or ortho para directing. Alright. So this will make the base foundation really strong of us to delve into the deeper discussion and solve further problems. So we'll start to taste the real organic from now.